Okay, welcome to section 10.3. We're going to take a look at multiplying radical expressions and just a few rules, or what they call the product rule for radicals. And so if you have two radicals that are raised to the same root, most of the time this is going to be just the square root, so you won't see anything present here. And you multiply them together, it's just simply going to be the product. And this is something we'll often do to simplify our radical expression. Sometimes what it may also come down to is we may want to pick apart a number that may have two factors that we can simplify in this way. So it's important to be able to utilize this property back and forth. So one way we can do this, for example, is let's say, for example, I have the square root of 12 times the square root of 3. Again, since I'm using a square root, there's going to be no number here for this. Well, I can go ahead and I can write this as the square root of 36. Not terribly helpful unless you recognize, of course, that the square root of 36 is equal to 6. And then, this all simplifies quite nicely. So something else that we could do is we could start with something like, let's just start with the square root of 36. And this is just an example. Well, one way I could do this is I can write this as a square root of 9 times the square root of 4. And you probably know that the square root of 9 is equal to 3. The square root of 4 is equal to 2. And you probably know that 3 times 2 is equal to 6. So, yeah, I still get the same thing in this process here. Just depends how you work with all of the numbers. So, we're going to use some of these properties today, and we're going to learn how we can not only utilize these, but then also simplify and then multiply radical expressions together. So, let's go ahead and just take a look at some basic multiplication problems here. This is going to be question number 7, or question number 8, I should say, where I have radical 10 times radical 3. So all I'm going to do is simply multiply the numbers that are under the radicals. There are both square roots, so that's not an issue. It's going to give me the square root of the product of 10 and 3, which is just the square root of 30. Just to reinforce this idea of making sure they have the same root a little more, let's go ahead and take the cube root of 2 times the cube root of 5. And I'm going to write this as a cube root again. Don't forget this, please. And 2 times 5 will equal 10. So my final answer to that is going to be the cube root of 10. So the next problem we're going to do is go ahead and we're going to tackle question 12. And we're going to take a look at the fourth root of 8 times the fourth root of 9. And if I just multiply the two numbers together, I'm going to get the fourth root of 72. So you'll notice here that we do multiply 8 and 9 together, but we don't change the root on the radical. So let's start taking a look at some more complicated expressions that do contain some variables. So one such example of this is going to be question number 15. This is going to be the fifth root of 8y to the third times the fifth root of 10y. And all we're going to do is we're going to write down the fifth root again here. And this is going to be 8 times 10, so that's going to be 80. Y to the third times y would be y to the fourth. So we perform multiplication here like we would any time by simply multiplying the numbers together and then applying the rules of exponents that we learned. When we have y to the third times y to the first, we add the exponents together to get y to the fourth. Another interesting example, let's take a look at question number 18, where this is going to be x minus a under the radical here. And here this is going to be times the value of x plus a. So you may recognize that if you multiply x minus a times x plus a, these are usually the pair of factors we get for the difference of perfect squares. And in this case, we could simply write this in as the square root of x squared minus a squared. In this one, it is not necessary that you put parentheses with this. I just put them in there, but you could, if you wanted to, simply write this as x squared minus a squared, and that would be all you would need to do for that problem. Let's go ahead and take a look at another similar example. Let's take a look now at 22. So this is going to be the fourth root of x minus 1 times the fourth root of the quantity of, sorry, not x minus 1, I take that back, it's going to be x minus 2. Oh no, sorry guys, it is x minus 1. So it's x minus 1. I apologize for that. But let's go ahead and take a look now at x squared plus x plus 1. So one of these, that's really tricky. You may or may not recognize these, but if you multiply these together, you would in fact get, these are in fact the pair of roots for something that's known as the difference of perfect cubes. You may recall we learned that type of factoring in Chapter 7. Here that factoring now is coming back again, except that this is in the form of multiplication. If I multiply x minus 1 together times x squared plus x minus 1, which you can do for yourselves by putting it in the box here, x squared plus x plus 1 over x minus 1. Let's see what result we get. X to the third plus x squared plus x. This would be minus x squared minus x minus 1. These will reduce, giving us x to the third minus 1. And that is why when we factor the difference of perfect cubes, we get these pair of factors. It works. So that is one way in which we can simplify it here. So let's go ahead and take a look at maybe just one other type of problem. I'll do that on the next page here. I'm going to go ahead and take a look now at 25. And it's going to be a problem that looks like this now. 7th root of x minus 3 over 4 times 5 over, or the 7th root of 5 over x plus 2. So remember, we are multiplying these quantities underneath. We are not adding these quantities underneath. So what might make this a little easier is to kind of do the work underneath one radical. So it's going to be x minus 3 over 4. And what is it being multiplied by? This is being multiplied by 5. 4 is multiplying x plus 2. So let's see if we can simplify this a little bit as the 7th root of 5x minus 15 over 4x plus 8. So we just multiply everything together to get the 7th root of 5x minus 15 over 4x plus 8. So multiplying like we've always done here, just throwing in some radicals into the mix. Now we need to take a look at something quite different. And this is simplifying radicals. Probably something you haven't been asked to do quite before. But when we simplify them, we aren't always going to have the radicals disappear entirely like we did in the previous sections when we looked at radicals. So we're going to begin to take a look at question number 28 and see how we can simplify the quantity of radical 50. So there are a couple of techniques for doing this, and depending on your comfort level with these techniques, you can choose which technique to go with, and let's see what you do. So one technique is to go ahead and take 50, and what I'm going to do is I'm going to break this down into two factors underneath here. So one may recognize, well, hey, 50 is 25 times 2, and 25 is a perfect square. So taking advantage of the property we learned earlier in the lesson, we can go ahead and write this as radical 25 times radical 2. Well, the square root of 25 is equal to 5. Radical 2 I can't simplify at all, so my final answer can be simplified in the form of 5 radical 2. So what's really important to know for this is to know what your perfect squares are. If you know what your perfect squares are, this technique is not going to be terribly difficult. If you don't know your perfect squares, you'll probably find this aspect of the lesson to be challenging. But let's go over another technique for this. So one other thing we can do with the square root of 50 also is I can write this as the product of prime numbers. So I can take 50 over here, and I can do what's called a prime factorization tree. 50 I can write as being equal to 25 times 2, and then 25 as 5 times 5. So one thing about this is you need to recognize what prime numbers are. So I'm going to write this as 5 times 5 times 2. And I have a technique which is called the jailbreak method. And it works like this. You have people, they want to break out of prison. They only work with pairs, and they only work in the same gangs. And here we go. We have a pair of 5s that want to break out of prison. So what will happen is that one will need to hoist the other person up. Well, that one's going to go ahead and get out, while the other one gets shot from the guard tower. So that's going to be 5, and then this is going to be reticle 2. This one is killed. The 2 is simply stuck inside. It can't get out. So final answer again is going to be 5 reticle 2. So I will use this method a few times in the course of this lesson here today, especially once we start working with variables to see what this is going to look like. And hopefully this will help some of you out in having some technique to approach this with. Question number 30. This is going to be the square root of 45. So some of you will recognize in this one that I can write 45 as radical 9 times 5, which I can express as radical 9 times radical 5. And the reason 9 is important is because 9 is a perfect square. I could write this as 15 times 3, but that doesn't help me at all because neither of those are perfect squares. But the square root of 9 here is 3, and then I bring down the radical 5, and there would be my final answer. Another technique again, using the jailbreak method, would be to take 45. Let's say I did write it with 3 times 15. 15 I would write 3 times 5. My prime factors would be 3 times 3 times 5. So I have my pair of 3s that want to break out of prison. One 3 gets out, the other gets shot, the 5 stuck inside. So my final answer is 3 radical 5, just like I got over here. So you have to be comfortable with this technique and practice this, practice this, practice this. It will begin to make sense as you do a little more of it, but it does require practice, especially once we start doing work where we have to simplify expressions that contain variables, which is what we're going to be getting to next. 32. So here we have the square root of 75 y to the 5th. So as we get this, 75, the square root of 75y to the 5th, well, one way we can break this down, I can write this as the square root of 25 times 3, and then y to the 5th is not a perfect square, but I need to be able to write y to the 5th that is the largest even exponent times just an odd number. So I can write this as y to the 4th times y. Now, we could break this down even further, but we could write this as radical 25 times radical 3 times radical y to the 4th times radical y. So when we look at this now, the square root of 25 you should probably know is going to be 5. Well, what's the square root of y to the 4th? Well, we've been working with rational exponents, so another way to look at this is to write this as y to the 4 over 2, or just y squared. So this has a perfect square, which is why we want the largest even exponent possible, because when we win, we rewrite this as a rational exponent. I can simplify it very easily to get y to the 2nd. So we've simplified this part, we've simplified this part, but the radical 3 and the radical y doesn't simplify, so I'm just going to leave it underneath. And I come up now with a final answer of 5y squared times the square root of 3y. And that is as simple as I can get this answer. We're going to go ahead and show you a few more questions for your consideration and see how you handle them. You may, if you want, stop the video to try these on your own at any time. Let's take a look now at 38. We're going to have the cube root now of 27ab to the 6th. Now, for this one, we're looking for things that are perfect cubes. So, and when we break this down, I'm going to write this now as the cube root, well, let's see. yeah, I'm probably just going to leave it as that, but let me just break down the three radicals here. So cube root of 27 times the cube root of a times the cube root of b to the sixth. And let's see what simplifies. Because I don't need to factor anything here, I just need to separate it out. The cube root of 27, 3 times 3 times 3, that's going to be 3. Cube root of a, I can't simplify, so I'm going to go ahead and leave that as the cube root of a. The cube root of b to the sixth, if I write this as a rational exponent, I write this as b to the sixth over 3, which is going to give me b to the second. So when I put all this together, I'm going to write this now as 3b to the second times the cube root of a. And that is my final answer as much as I can simplify it for this activity. Let's take a look at one final question. We're taking a look at question 40 before we wrap up this first half of the lesson here. So for question 40, we have the cube root of negative 32 a to the sixth. So you may or may not know that 32, negative or positive, and because of the third root, the negative doesn't matter, that negative 32 is not such a big deal, okay, because it's an odd root, but negative 32 is not a perfect cube. So we need to find some factor of 32 that is a perfect cube. So we will be splitting this up a little bit in the following way. So I'm going to write this as negative 8 times 4, because negative 8 is a perfect cube. Its cube root is negative 2. And I'll just write this as a to the sixth, putting the cube root here. Now I'll break this up into the cube root of negative 8 times the cube root of 4 times the cube root of a to the sixth. So the cube root of negative 8, well, that's going to be negative 2, because negative 2 times negative 2 times negative 2 is negative 8, times the cube root of 4, which cannot be simplified. But if I take a to the sixth and I write it as a to the sixth over 3, that's going to give me a to the second. So I'm going to put all this together to get negative 2a to the second times the cube root of 4. And that is going to be my final answer in the simplest form. That is what we're doing up to this point. We will resume with the next lesson here in a moment.